Good morning, and welcome to another episode of The Rollup. Today's guests are Uma Roy from Succinct and Brendan Farmer, co-founder of Polygon. Today we're talking about the integration between Succinct's ZKVM called SP1 and Polygon's aggregation layer. The SP1 makes it easy for developers to use Rust and incorporate ZK proofs into their applications. And Polygon's aggregation layer is utilizing SP1 for seamless, quick, and affordable interoperability between chains connected to the AggLayer. Hope you enjoyed today's episodes. Before we get into it, a word from our sponsors. Enjoy. Welcome aboard on our journey into the singularity. This is the endgame roadmap for Frax and Fractal, the new L2 out of the Frax ecosystem that is totally based on fractal scaling. Fractal is a modular L2 blockchain built by Frax with modular and fractal scaling in mind. Fractal scaling is based on the Mandelbrot set of fractal images, and it explains how L2s become L3s and the entire app chain lifecycle goes through its evolution. The Frax ecosystem is made of some of the top builders in the space and has stemmed from its OG days of the Frax stablecoin. It is now in the LST space, the LRT space, and this Fractal L2 joins the existing suite of Frax products, including Frax Swap and Frax Lend. You can see Frax Ferry, the bridge to go from any chain, Arbitrum, Optimism, or mainnet into the Fractal mainnet. Bridge your tokens and bring your Frax assets into the Fractal ecosystem. Join today to get the best out of Fractal. You are still early. Join today. Take part in our expedition into the singularity.
What's going on, guys? Welcome back to the Rollup. Today we have our friends Uma and Brendan to talk about the recent collaboration between Succinct and Polygon. A lot to talk about there. Today we have, of course, Rob here with our new look on our white text. What's going on, Rob? How you doing, man?
Feeling good. Feels like we're back to the future or something. We had white text and then it went somewhere and now we're back. And feels good. Talking about back to the future, ZK endgame feels like the future. And so we're going to talk about that. Yeah, absolute pleasure. Thanks for coming on, Uma and Brendan. And pretty stoked to talk about ZK. It feels like we're inching ever closer to like this futuristic world where ZK is real. So I guess maybe that's the first question that I'll pose, open-ended. Is ZK real?
I think it's been real, Robbie.
Yeah, I think that was actually a little offensive to Brendan.
No. It's actually like hard for me to actually get really offended, although anyone following my occasional Twitter battles might think differently. But I mean, I think it's like the question is like ZK for what? And I think ZK is sort of like progressing along this frontier where as we move forward, like different things become possible and become practical with ZK. And so I think, Uma and the Succinct team are like continuing to push that frontier. We're pushing that frontier. And so I think like, ZK for a single rollup has been practical for a little bit. It's getting better. And I think a big part of what we're going to talk about today is like how we're continuing to push and like what we see kind of being on the horizon for what's possible with ZK.
Awesome.
Yeah, we should lay the groundwork a bit here for like what is kind of coming out of this collaboration. Rob skipped intros. We'll pass it over to Uma and kind of maybe brief our audience on Succinct and kind of this idea of ZKVMs. This is your first time on the Rollup, so I think that'd be helpful to kind of lay the foundation here.
Yeah, for sure. So yeah, I'm Uma. I'm one of the co-founders of Succinct, and we've been working on a ZKVM called SP1, which you kind of alluded to. And yeah, maybe to talk a little bit about what a ZKVM does. ZK has been real for a very long time. Like Brendan has been working on it, I think, at this point for maybe like 5 years, I want to say, maybe longer. So it's always been real. I just think it's always been very difficult to use. you'd have to have a genius like Brendan or other people who with like a strong cryptography background, really strong engineering background, making all these like custom circuits or diving into these like really weird arcane ZK languages or libraries. And with the zkVM, what it lets people do is it lets normal developers write regular Rust code and then just use ZK. So it makes ZK a lot more real for a lot more developers, I would say. And that's kind of like um, we hope is a new frontier in like ZK accessibility and then also adoption, because now it's just become like 100x easier to use with what we're building.
Awesome. I feel compelled just to give a little bit more context around my question. We had just done a ZK and Bitcoin live stream. And so on Bitcoin, there's no ZK verifier. And so it's not real yet in Bitcoin, but certainly has been real for a very long time in the Ethereum space and beyond. And so that makes a lot of sense. All right, Brendan, do you want to intro yourself and Polygon AggLayer?
Yeah, sure. So, I work at Polygon. I work on ZK R&D stuff. Prior to that, I was at this project called Mir that I started with Daniel Lubarov. And yeah, I guess the AggLayer is our effort directed at solving the fragmentation problem on Ethereum. So I think it's fairly well understood now. We've been talking about it for a long time. Like, there are a bunch of different rollups on Ethereum, and so we have all of this like block space that's sort of like floating above the Ethereum L1 that people can use. But the problem is, like, when we talk about scaling, what we really talk about is like scaling access to shared state into liquidity, and we don't have that. Like, each individual L2 can have like some value, can have some liquidity, it can have some shared state. When you think about what's required to like move that value between L2s, it doesn't really like make sense from a scaling perspective. It's like, for optimistic rollups, you have to wait 7 days to withdraw. For ZK rollups, you have to wait maybe 30 minutes. And so the AggLayer is like designed to provide two things. It's designed to allow L2s to have asset fungibility. So the idea is that I should be able to take my ETH that's on Polygon zkVM and move it to OKX's XLayer chain, and I should get ETH. I shouldn't have to worry about like wrap synthetics or using market makers to like swap between versions of a token. And the second thing that it provides is like really, really low latency interop. So I should be able to do this really, really quickly. I should have asynchronous and synchronous composability across chains. And we think that these two things will allow us to sort of like stitch together the L2 ecosystem into something that feels like using a single chain, so that we can actually achieve scalability and like achieve parity and surpass other L1s like Solana or others that offer a more scalable environment now. But we think that Ethereum can become sort of the end game in the future.
Yeah, I don't know if you saw Vitalik's meme post today, but he had kind of like the thing, like the guy from the movie with the scary mask knocking down all those doors. And the next door is the cross-chain UX interoperability door that needs to get knocked down. So yeah, it's going to be an exciting race.
Yeah, I mean, we're working on it, but
Yeah. So let's talk about why AggLayer is a beneficiary of ZKVMs and kind of like why being able to do things in Rust from your perspective on this, goal to achieve interoperability is extremely important. And I think that we can dive more into some of the technicals on the pessimistic proof side of things as well. But broadly, like, why does AggLayer need ZKVMs and like what capabilities does Succinct bring for AggLayer?
yeah, sure. So I can say a little bit, but I don't want to monopolize the conversation. I guess for some context, we built this ZKEVM, and we did it with custom circuits, or like what we call like custom coprocessors. And this was a really painful and lengthy process, and it took us a long time. But we had this issue where we could achieve performance, but at a great cost in terms of like developer time and auditability and all that stuff. And so with the AggLayer, we need to prove things to L1 that allow us to provide these safety guarantees that we need to solve L2 fragmentation. And we really wanted to avoid writing a bunch of custom circuitry. And so we sort of had, like, on the one side, we had this desire to write things in like Rust or some, well-known general purpose language with really good tooling. And on the other side, we had Plonky 3 that we've developed. It's this, innovative proving system. I think it's one of the fastest options, if not the fastest on the market now. And so we had this gap where we really didn't want to write custom circuitry, and we really wanted to target Plonky 3. And we didn't really have a good way to like get there. And fortunately, Uma and the amazing team at Succinct developed SP1, which is basically like a library or a tool that like allows us to get from Rust code to Plonky 3 in a really, really nice way. And so it was just like a really natural, I like the partnership doesn't end with us using SP1 for the pessimistic proof. There's like a lot of collaboration that's going on right now, but this was something that was really, really important for us to unlock developer velocity and actually shipping the AggLayer.
Yeah, to elaborate on that, I think the hard part about building something like the AggLayer is actually building like the protocol, designing the pessimistic proof, figuring out how all those chains are gonna like connect and tap into the liquidity, and then also even going out there and like doing BD and like getting those chains to sign up for something like the AggLayer. And I'm kind of the opinion that, very smart people like Brendan or like, Sandeep at Polygon, their brain power is probably best spent thinking about, how do we actually improve the user UX and not spent on, oh, how should we, spend thousands of engineering hours handwriting this like small circuit to enable like the actual protocol we designed. So I think it's like safe to say that because they could just write the pessimistic proof program after they'd like come up with it in their heads in normal Rust code. It was like, I think 2 engineers on the Polygon team wrote it in like 1 or 2 weeks. And I think a similar process without something like SP1 or a ZKVM, where you had to like basically handwrite all the circuitry, would have probably taken like a much larger team months or something like that. So I think it really unlocked their developer velocity, and I think also probably freed up their mind space to think about the actually important things that matter in the AggLayer protocol. And from my perspective, I think the AggLayer is actually a really well-designed protocol. I think it makes like a ton of sense. I think it's like a very elegant solution to enable a bunch of different stacks to connect and talk to each other and interoperate. So it's not just only Polygon CDK chains can talk to each other via the AggLayer. It's actually like any stack. There's going to be like some exciting news soon about even non-rollups being able to connect to the AggLayer. And yeah, just being able to have all the ZK stuff for that as almost an afterthought, like, oh, we dreamed up something. Okay, cool. Now we can just code it, write it, and use SP1 or ZKVM. I think it's kind of game changing in terms of freeing people's mind to design like protocols the right way, and enabling interoperability across a bunch of different stacks in the way that it should be.
Yeah, I would just add, like, from an audit perspective too, like it's so daunting to undergo an audit for custom built ZK circuitry and being able to like audit. So obviously Plonky 3 needs to be audited and Succinct needs to be audited, SP1 needs to be audited, but that happens once. And being able to audit Rust code is just like such better model for being able to not only build the protocol, but also to be able to like iterate on this. Like that's something that we are really focused on, is like, how do we shorten the cycle of like development and iteration, so that we can build better products. And like SP1 is such a core part of allowing us to do that.
Yeah, even on our side, we had written a Tendermint light client. So Tendermint's this consensus protocol. We had written a light client for it using custom ZK circuits on our own team. And that had taken a team of like 3 or 4 engineers, like many, many months, and like a lot of heartache, many thousands of lines of code. And yeah, it's like very hard to understand what's actually going on. And then with SP1, we'd written the same Tendermint program in like, I think 50 lines of code in literally like a weekend. So you turned like months and thousands of lines of code into like a weekend project. And I think it's just better for upgradability, auditability, understandability. Now like any developer on our team can like take that and iterate with it. So it just seems like totally the future of how ZK is going to actually get used, just because it's like 100x easier.
Love it. So that we have this kind of broad understanding here of this compatibility with SP1 and ZKVMs and kind of how this interoperates with AggLayer. I'd like to go a little bit deeper into like some of the core functionalities of AggLayer, and of like just the ZK interoperability, and specifically kind of touch on some core areas where SP1 and this kind of Rust programmability makes that process much easier. So, Brendan, maybe you could shed some light on some of the proof generation or verification, or kind of where there is a need in the AggLayer kind of network, if you will, for ZK, and then kind of how using SP1 makes that process easier or faster, cheaper, and feel free to get into the weeds a little bit.
Yeah, sure. So I guess for more context on the AggLayer design, the AggLayer is designed to be used in, like, as Uma said, like a heterogeneous environment of VMs. So the idea is like anyone should be able to bring like an EVM or an SVM or even like some custom Rust VM that they build from scratch. And they should be able to connect to the AggLayer and to connect to this like pool of unified liquidity. The problem there is like, if we just stopped there, that would actually be super, super dangerous, because it means that any chain that has an unsound prover or is sort of compromised by an attacker could potentially like create a transaction that would maybe drain like 1,000,000 ETH from this chain that actually doesn't have 1,000,000 ETH deposited. And the because the prover is unsound, a proof could be generated for that transaction that can be verified by the AggLayer, and it looks like it's a valid proof. But that would involve like draining this shared bridge of funds, and would reduce the security of the entire ecosystem. And so what the pessimistic proof is basically saying, okay, from the AggLayer's perspective, we don't assume that any of these chains have a valid prover. Instead, we look at the asset transfers that are handled through this unified bridge, and we make sure that that no chain can withdraw more funds than it currently has deposited to that chain. And so in this way, we can guarantee that like even if a chain has an unsigned prover, or if it's compromised and it is able to submit an invalid state transition, that doesn't affect the security of the entire ecosystem. And so this specifically is what we're using SP1 to prove. So we have some Rust code that encodes the logic that we're trying to enforce here. We use SP1 to generate a Plonky 3 proof for that program or for that logic. And so similarly, when we think about like that sort of takes care of this like asset fungibility side of the unified liquidity picture, where we are able to safely use a shared bridge across a bunch of different chains. And when we think about the other side of that unified liquidity picture, it's really low latency interop. And so what we need to do there is allow chains to interoperate safely, even at lower than Ethereum latency, or lower than Ethereum finality latency. And so what we need to do there is we need to check basically that like when chains are depending on states from different chains, or when chains are like synchronously passing messages during the creation of a block, that they're actually relying on like the correct state of the world of another chain that's settled to Ethereum. And so we'll also use SP1 for that. So we can enforce that like even if chains are interoperating at lower than Ethereum finality latency, that they can't rug each other by equivocating or sort of behaving maliciously.
Very cool. Could we just kind of double click on that? Because I think low latency interop is something that like everyone wants. And so how are you able to achieve this faster than Ethereum finality, and then execute these cross rollup transactions? Like, the confusion in my mind is like, well, if this blockchain over here has a 30-second block time and this blockchain over here has a 5-minute block time, how are we able to synchronize the state of those chains so that one blockchain relies on the other, and they can kind of like understand where each other is at? If that question makes sense.
Yeah, so I think so. We'll see if my answer makes sense. But so the problem that we're trying to solve is like if you have two rollups, and one rollup maybe sends a message to another rollup. So it says like, okay, I'm going to transfer 100 ETH from, or this user is transferring 100 ETH from, chain A to chain B. And chain B says, okay, I've received this message from chain A. I'm going to mint 100 ETH on chain B. But then this is all happening before, the states of either rollups or either rollup is finalized on Ethereum. And so what chain A could do is it could say, okay, I'm generating this valid block that includes this this burn 100 ETH transaction, and I'm going to include the block and the message that it sends to chain B I'm going to prove it, and I'm going to send that proof to chain B. But what I'm also going to do is I'm going to create another block that equivocates and doesn't include that burn transaction. And that's the block that I'm going to send to Ethereum. And so what happens is chain B is rubbed. It has more ETH on the chain than it has collateralized in the bridge. And so what the AggLayer is designed to solve is to basically ensure that chain B is only settled on Ethereum if the state of chain A that it thinks is valid and is the right one is also settled on Ethereum. And so you might ask, well, okay, what happens if chain A equivocates? And then there's some delay in finality for chain B, and chain B has to reorg. But this is the sort of the fundamental limitation of the choice that chains have to make between, I don't know if it's right to say between safety and liveness, but between guaranteeing that they'll never be equivocated and guaranteeing that they'll never reorg. And so we can extend this case to sort of more elaborate situations where maybe chain A and chain B they share a block builder, or they're both using the same shared sequencer or shared proposer, and there's a single block builder that's synchronously building blocks for both chains, and they're sending messages within the construction of a single block. And the AggLayer can enforce that actually those messages that are received during block building are consistent. So, both chains can safely rely on this shared block builder without actually having to trust the shared builder. And so as far as having different block times, in sort of the asynchronous case, the chains would just need to wait for, if you're accepting a message from a chain that has a block time of 5 minutes, the delay on that message would be 5 minutes, or whenever the chain's block is created. But so I Uma also is I think an expert at sort of cross-chain interoperability and stuff, and so I'm sure she has stuff to add here too.
Actually, a question for you, Brendan. Is the AggLayer offering a fast finality DA layer as well, or how does that get settled?
No, so we the way that we conceive of the AggLayer is the thing that we are building is just this kind of cryptographic safety guarantee. So we're saying okay, once chains have coordinated and have submitted blocks, they can take their proofs and their blocks and submit them to the AggLayer, and the AggLayer will prove that the bridge invariant is preserved and that cross-chain interoperability happened in a way that's consistent. In terms of what they rely on for actual block creation, it's kind of up to the chain. So they could rely on Espresso. Espresso has this sort of early I don't know, pre-confirmation or finality guarantee that exists, and chains could opt to rely on that, or they could use a different guarantee. And so from the Polygon perspective, the part that we are building is intentionally, I think, very minimal, and it's just designed to provide safety around the bridge and interoperability.
Oh, I see. So it's kind of up to the chain to decide how they're going to receive messages from other chains or get shared sequence with other chains and stuff like that. Yeah, makes sense.
Exactly.
Brendan's been practicing his podcasts.
Yeah, I mean, you'd think that I would be smoother at this point after how many podcasts I've done, but every time I'm I need to think what the.
Oh, no. Yeah, I was gonna say I really like the AggLayer design because I think it's agnostic to what stack you're using. You could have an OP stack chain or an Arbitrum, I think, Orbit chain, or you could also have a Polygon CDK chain. And it sounds like if they conform to these APIs, they can kind of pick and choose, like, oh, what sequencing am I going to do? What DA am I going to use? And then they just generate their proofs and then submit them to AggLayer, which makes sure a bunch of like basically invariants hold true across interop, and then all these chains can talk to each other. I think it's a very smart design. And yeah, it seems like a lot better than being really rigid and saying, oh, only if you use this stack can you interoperate. It's more like just an API for fast interoperability.
Yeah, I agree. And I think that was like very intentional from our part, because we could have said, okay, like this is only available to CDK chains, and you know, we're going to sort of build this walled garden. But I think very much for us, it's like, okay, if we can get Ethereum to its next phase, where it has like clearly, I think, won, and like all of these scalability critiques are no longer valid, then that's going to be like so much better for everyone involved in the Ethereum ecosystem than if like we can sort of, you know, by ourselves, like control the like Ethereum execution layer of the execution environment. And so, yeah, I mean, I don't know, for from my perspective, it's about like growing the pie and like making, like getting to like past these infrastructure limitations that have been a problem for as long as I've been in crypto. And then we can, you know, figure out how, like what Polygon's role will be in terms of like providing chains and stuff. But I think like being like heterogeneous execution environments sort of make sense, because like all of the stacks that you identified are EVM based, like CDK and Arbitrum and Optimism. But I think that there's a lot of room for non-EVM execution environments, and I think that we want to support this. Like even I think even like custom Rust environments that are using SP1 for proofs. That's like an awesome idea. Like if you have a DEX and you don't want to pay the overhead of using the EVM or the SVM, you just want this like custom DEX that you've written in Rust that's super performant, and you get proofs for free from SP1. Like that's a really cool model in my mind.
Yeah, totally. That makes a lot of sense.
Yeah, we've been supporting that for a while now. It's like some of the Ethereum people get a little upset, but it doesn't really make sense to just kind of stick to the single execution environment. Although we've been kind of getting pushback on the terminology now from those who are also bullish with us, because they're called alt VMs, like ALT VMs, and so now they're supposed to be named next gen VMs. So as a shot to Ethereum. But
Yes.
Uma, I want to pass it over to you to talk a bit about some of the tech as well from SP1's perspective. I may butcher this name, but you guys have an interesting precompile. I think it's called KCAC. If not sure how you guys came up with that name, but yeah, maybe you could talk a bit about that and kind of the performance capabilities there on that specific precompile.
Cartesi is your home for app-specific rollups. At the forefront of developing new tools and platforms that enhance the capabilities of blockchain technology, Cartesi enables applications that are flexible and built to scale. Build on a full Linux environment and use traditional software libraries, but in blockchain development. Go to cartesi.io, that's cartesi.io, to learn more about building your own app chain today.
Yeah, I think you're probably referring to the Ketchak precompile, which is this hash function that's commonly used in Ethereum. So yeah, for some background, basically Ethereum has this hash function Ketchak that's used in computing its like state root and like state commitment and things like that. And then the AggLayer uses Ketchak to verify a bunch of Merkle proofs and verify, you know, state accesses for computing that all the balances are basically netted out evenly. Now, historically, Ketchak has not been like very friendly inside a ZKVM. So it'll take a lot of cycles, it'll be very expensive to prove, and overall, it'll end up being like a bottleneck in terms of proving time and cost. As one of SP1's very novel kind of breakthroughs was this precompile centric architecture, where basically we can take a really expensive function like Ketchak that's called very frequently inside some program you want to prove, and we make it a precompile. So it's kind of similar to writing like custom handwritten assembly, for example. So you kind of write this ZK version of assembly, and then you can really accelerate proving of Ketchak within our ZKVM. So in all, like it improves performance by maybe like 4 to 5x. In some cases, it can even be much more like 10x. But you have these precompiles that let you do things like expensive hash functions like Ketchak or SHA, or verifying signatures like SecP256K1 or ED25519 signatures really cheaply, even inside our ZKVM. And that's what gives SP1 its like really blazing fast state-of-the-art performance. And I think why it's relevant to AggLayer is that they did have a lot of Ketchaks in their programs. So I think without the Ketchak precompile, maybe using a ZKVM like SP1 wouldn't really have been feasible. Like it would have been too slow or too expensive. But with Ketchak, their program runs like just fine, and the proving time and cost is pretty cheap.
Yeah, we're us in the ZK community that are working with the EVM are still paying for the sins of Gavin Wood in terms of the choice of hash function and encoding and MPT. So that's just like something that we have to deal with.
Is there any data to like the scale of proofs and like how much this is costing right now? Because I imagine like Polygon AggLayer, especially in a more like fully fleshed out form, is going to be generating lots and lots and lots of proofs. So what is kind of the economics around this proof economy right now, and how do you see this playing out?
Yeah, it's a good question. I think for us, the proofs right now for Polygon, I mean, they haven't finalized their program or things like that, are in like the cents. So it's really cheap. I think it's really already like very cost effective. I think one really interesting thing for us we found is that our proof costs with the ZKVM and our precompiles actually are very similar to the proof costs in our previous circuit-based world. So even, for example, for our Tendermint program, we had written this custom handwritten circuit, and that had a proof cost of like tens of cents. And then in our ZKVM world, that also has a very similar proof cost, just because like our precompiles are so efficient. And then Plonky 3 is like super awesome. So like Daniel and Brendan and like the rest of the Polygon 0 team went crazy with Plonky 3. They have a lot of great optimizations, and that enables actually it to be very fast and very cost effective. And I think the mental model for cost is like already a lot of these proofs cost like cents, so it's like totally doable. We have some benchmarks suggesting even for like a ZK EVM, so like you take something like ref, you run it in SP1, it ends up being like a couple cents per transaction. All that stuff's going down like, month over month by like 2x, 5x, 10x. Like I think in 3 months that number will go down by 10x because we'll have better algorithms on our side. We'll have implemented, GPU versions of our prover or more optimized CPU versions of our prover. So yeah, I think cost is really point in time, and already it's really effective today, but that number's just going down more and more.
Yeah, the way that we model costs is like we just look at what users are currently paying, and then if we can get within like under 10% of that in just the proving component, then we think that's like a reasonable sort of short-term metric for practicality. And I totally agree with Uma. I'm not sure that people are aware of this yet, but we actually haven't really optimized Plonky 3 like to the same level that we optimized Plonky 2. And so like a lot of people on the team are about to kind of go crazy with reducing Plonky 3 proof cost. And so I think that will just be a really nice way to further decrease cost.
Very cool. Quick joke here is that like, Moore's law is supposedly breaking. So now we have like Uma's law or Brendan's law, where the cost of ZK proofs actually cuts in half every year. No, but they're okay. So I have another. I've got a question. It's like a 2-part question, but this might be a totally silly question, or maybe this is like really relevant. Which is that we've like seen a lot of these analogies for blockchains going into like compute, and how if we can provide verifiable compute on par with like cloud compute, there could be a real like mass migration away from cloud compute onto verifiable compute. I think the realization is that like, well, that would only happen if there's an incentive to do that. And there's an incentive to do that if verifiable compute becomes more affordable than something like cloud compute. And so I feel like, okay, so just with that frame, there's another framing where it's like, well, similar analogy to optimistic rollups and ZK rollups. There's only like, if ZK rollups are more affordable than optimistic rollups, then we'll see a mass migration from optimistic rollups to ZK. And so is that like a fair analogy? And do you think that there is a world where ZK becomes affordable enough that it makes ZK rollups more affordable than optimistic settlement, and then it makes verifiable compute more affordable than cloud compute?
Well, Robbie, do I have your permission to just go off for a moment?
If I offended you in the beginning part of this podcast by saying
No,
now's your opportunity to take that.
So I would say, so this is like a pet argument for me that I feel very passionate about. And that doesn't even matter because it's like empirically true. Optimistic rollups, they're actually already more expensive than ZK rollups because people look at the cost of optimistic rollups and they just look at transaction fees that are explicitly borne by users. But if you look at all of the fees, like, let me back up. There's this cost that users also bear, which is they bear like the capital inefficiency cost of having their funds locked on an optimistic rollup for 7 days to withdraw via the native bridge. And so if you look at all of the money that users have paid to skip the 7-day withdrawal period and withdraw via a third-party bridge, it's like $40 million on Arbitrum. And the cost of just proving every transaction on Arbitrum from Genesis is like 1/100th of that. And so, and like that's going down, like Uma said, that's going down like by 2x or by 4x, like every month. And so I think that we can already say that if you look at if you take a holistic view of cost, then optimistic rollups are already far more expensive than ZK rollups. I think that what's held back ZK rollups so far, and I'll cop to this for Polygon, is just like the tech has not been that mature on the client side. So the prover actually works well, like the cost is good, but we made some decisions, on the client side that we're undoing, and that's led to like a subpar user experience. But once we get to sort of maturity and parity in terms of UX, then I think that you'll see like ZK rollups like really, really start to take off because, especially if you think about like the fact that we're moving to this multi-chain ecosystem, being able to bridge funds instantly without dealing with a withdrawal delay for a challenge period, that's like a much, much better user experience than an optimistic rollup.
Yeah, if I may add to that rant, I like totally agree with Brendan. I think like ZK is like the only true form of scaling. Like optimistic stuff, I think just doesn't actually really scale that well because we have this whole fragmentation problem. Like how many times have you tried to use a rollup and then you're like, oh, I have my money stuck on another rollup. Okay, now I have to go to a bridge. Okay, now I have to find the bridge with the lowest fee. Oh, then my money takes like 15 minutes to appear on the other side. Like that sucks. Like that's not sustainable. And I think ZK is like the only way Ethereum is actually going to scale. Like that's why it's the end game. That's why Vitalik's super bullish on it. That's why it's like, and if you actually think about it from like a holistic perspective, ZK is verifiable compute. Like it is literally scaling. Like the optimistic stuff is not really scaling in the same way. You have to have people also running the nodes, like redoing the computation, re-verifying it. So I think ZK is like the only way any of this is actually going to work. And I think the thing holding back ZK, I think cost is actually a bit of a myth. Like as Brendan said, actually today optimistic rollups have a lot of hidden costs that are kind of like disguised and shoved under the rug. And the ZK stuff is already actually really cheap. So I actually don't think the cost is maybe even that much of an issue, although in the public eye I think it is. I think the real thing holding back ZK today is like the developer burden. For example, if you're like a founder of a ZK rollup, you have to spend basically 80% of your time being like, oh God, like how do I think about my ZK proof system? Your best engineers on your team are probably, spending time working on all the ZK stuff. And I think that is like, a tough situation to be in as like a rollup founder, because really you should be spending all your mental cycles and all your creative energy on like, oh, how do I have the best ecosystem? How do I attract the best users? How do I like, think about the dApps and stuff like that? And so I think like with ZKVMs like SP1, where now if you're a rollup founder, you can use ZK as a total black box. You don't have to worry about upgradability and all that stuff. Like you can just write normal Rust. Okay, when Reth upgrades, you're like, okay, let me cargo update and improve, like bring in the latest version of Reth. Great. Now everyone, like the most creative BD people can also have ZK rollups. I think then that's when like ZK is really going to take off. Like it's going to be cheaper, faster, better UX, and also just really easy for developers to use. And like with that combination of things, I think it's inevitable that like every rollup is going to be a ZK rollup. I think there's no way that base doesn't happen. I think honestly, even in like the next year, I just see it happening. And maybe that's a contrarian opinion, but it's like one that I really strongly believe. Like when the usability and DevX of ZK gets good, which now I feel like it has with SP1, it's just going to take over everything. That was my rant.
I think not to like create like too tortured an analogy, but I think that there's like this interesting thing happening where right now, if you're like an app chain founder, to Uma's point, you have to think about like all of these like technological elements. You have to think about like, okay, like how do I build on ZK technology? And then you also have to think about, okay, like even beyond sort of my core competency of maybe building a DeFi primitive or building a game or building an NFT mint. I also have to think about like all of this like ecosystem development. So I have to think about, okay, how do I incentivize liquidity to like come into my marketplace? How do I bring users? How do I like, like connect with people that are like market making for NFT or for DeFi? And so I think like in the same way that like SP1 is trying to abstract away or sort of black box the technology, like the AggLayer is about abstracting away like all that ecosystem development. Like the idea is that like you should just be able to focus on your core competency, like the thing that you do better than anyone else, whether that's like again building a DeFi primitive or a game or like some social application. You shouldn't have to think about like, okay, how do I play these like token games to like incentivize liquidity to come into my ecosystem? And so I think we're like moving to this world in which like builders can actually focus on their core competency and their comparative advantage, and they don't need to think about these things that like maybe they aren't as good at, but are still like right now they're like essential and required for the success of their app chain. But in the future, like maybe they won't be, and maybe the only thing that will be required is like building a really cool game or a really cool DeFi primitive.
It's like you're wearing two hats. It's like or really it's a ton of hats. It's like you're a CEO or a founder, you're a marketer, you're a therapist sometimes to your employees, you're a CTO and more, and kind of being able to build on the best rails and eliminating that burden, as you guys are both alluding to, is like that takes the acceleration of ZK to like a whole nother gear. So yeah. Kind of wrapping up here, I think, Rob, do you have any questions that are on your mind here, or just kind of closing thoughts?
I guess like one thing that might tie into like the Plonky 3 optimizations is just kind of like what's left. Like ZK proofs are already affordable, and so like those can scale. So like what is there still to go here to really accelerate?
Yeah, so we think about cost in terms of like use case and application. And so again, like we spoke early in the episode about kind of pushing the frontier of practicality and making more things feasible and cost effective. And so right now, ZK is super practical for like transactions that have inherent economic value. So if someone's doing a swap, they're probably willing to pay like a tenth of a cent or like, a couple hundredths of a cent in proving cost. But if they're doing something where like an application where like transactions don't have like a very high economic value or an economic component on a per transaction basis, like playing a game or using some like social app, they might actually like not be willing to pay even a hundredth of a cent in proving costs in aggregate because they're submitting 1,000 transactions or something. And like it's just a game. It's not something that they want to like pay money for. And so I think the goal there is to just like push the frontier of applications that are cost effective and that sort of makes sense to be ZK rollups or on ZK powered app chains. And so that's what we're focused on with Plonky 3. In terms of the concrete optimizations, just a lot of improvements across the stack. So like we sped up the Poseidon 2 hash function by 2x. We're just working like at every level of from the IOP to hashing to LDEs and just focused on like squeezing every bit of efficiency like out of the underlying proving system.
Yeah, I would agree with that. Like, basically, I think the costs today are already cheap enough for example for Ethereum style rollups, where already the rollups are paying a lot to Ethereum for GA and like settlement and things like that. So I think already for a lot of those cases, proving even with the zkVM is kind of a de minimis cost relative to like the rest of costs of operation. But then as you make proving cheaper and cheaper, it kind of opens up the world of use cases. So you can imagine maybe even some Web2 company decides one day to put like a lot of their server code in a ZK proof. And like every time you interact with them, they also give you ZK proof that they're not doing bad stuff. Or like, I feel like there's a lot of like use cases like credit unions or things like that, where it'd be really nice to know that what they're doing is verifiable and they're not just, randomly saying someone's credit score is bad or things like that. And so I kind of view the evolution of ZK as crypto being like the first major use case, because it is this like already very expensive environment. And also like the overhead of decentralization makes it like a perfect fit for the scalability benefits of something like ZK. But then as the tech gets proven out here and iterated on here, and we're using crypto as kind of like our first customer, then over time we can even go to other applications outside of crypto, where when the costs get cheap enough, that also might benefit from verifiability. And that's also really exciting to me as like an area of ZK, is like how can it be used like outside of crypto as it gets cheaper and cheaper. So it's really just like opening up the frontier of like use cases that are possible, which is very exciting.
Yeah, and I would just add that we like we've spoken primarily about cost, but actually like latency does start to matter. And so like we spoke about the ag layer and sort of the risk of malicious chains causing reorgs. If we can shrink the latency at which chains produce proofs, then we can like minimize that risk or minimize that window when a liveness issue can happen. And so I think that's important. Same for like client side proving. And so I think you just start to see like different applications become possible, both from the cost and from the latency perspective.
Yeah, I know we say like instant finality when comparing to optimistic rollups, but like how much of the focus is going into also reducing that kind of time to verification as is going into the cost of generation and verification? Is it like half and half split, or is it mostly focused on cost right now and then going back to time after? Or how are you guys kind of thinking about that?
Well, I guess latency and costs are like related, because if you're spending less time, then you're also spending, less money for the CPUs or whatever hardware you're using. So they're very related concepts. Like generally when we speed up latency, we also improve cost and vice versa. Um, yeah, so I would say they're highly correlated in general. And I think we're at this stage where there's just a lot of low hanging fruit everywhere. I'm sure Brendan feels this way too, where like the Plonky 3 team feels like they have like 10 ideas for improving latency and cost and performance overall. We also feel like we have like, 10 or honestly a lot more ideas for improving SP1's performance. Yeah, so I think there's a lot of low hanging fruit everywhere, where we're not yet having to make the trade off of like, oh, we should improve latency at the expense of cost or something like that. It's like an overall holistic optimization.
Cool. Well, guys, thank you for coming on and talking about the collaboration, and congrats for that. Definitely had some really insightful takes, and always a pleasure. So thanks, guys.
Yeah, thanks for having me.
Thank you.
Onwards and upwards. ZK is real, Rob. I don't know what's going on there with Rob, but ZK is real.